Right, this is paper 2 from 2022 TMUA. Let's just do it. So question number 1 was asking about stationary points. So we're obviously going to find dy by dx. There it is. Dy by dx is 0 for stationary points. We can divide everything by 12. We can factorize out x, and we can then say that there's one solution. If x is 0, you get a stationary point. How many solutions do you get from this quadratic? Well, b is 1, a is 1, c is 1. B squared minus 4ac is less than 0, so this has no real solutions. And so the only stationary point is that x equals 0, and there was just one of them, so the answer is B. Question 2 then, so I did a bit of binomial to expand this out. I've just about memorized up to 5 is 1, 5, 10, 10, 5, 1, so I thought that was the quickest way to just write it out. And this is, of course, just x to the 0 plus x to the 1 plus x to the 2, and so on. Now, how do you get x5s out of this expansion? Well, you either do 1 times x5, or 5x times x4, or 10x squared times x3, and so on. So it's essentially just going to be 1 plus 5 plus 10 plus 10 plus 5 plus 1, which will give the answer of 32. Question 3 then. Anyone who watched my videos on this hopefully got this right. If n is prime, find a counterexample. If n is prime. If you're in assembly at school and they say, if you study English and you don't study English anymore, you stop listening. You don't care. The question isn't about you. If n is prime means that the question isn't about this because it's not prime, so we get rid of it straight away. N squared plus 2 is not prime, so let's work out 2 squared plus 2 and 3 squared plus 2. This is 6, which is not prime, which does the thing, so it's not a counterexample. This is 11, which is prime, and so it is a counterexample, and we have 2 only. Good. Question number 4. So this is a circle, so let's complete the square on this and this to make it sort of circular. So we get this, we can move that stuff over. Now, let's sort of draw this out. We've got a circle with center FG, or minus F minus G, I guess it doesn't really matter. And we've got another point at PQ, and it doesn't anywhere say that PQ is on this circle. It could literally be anywhere. So the distance between here and here is all to do with, of course, the distance between F and P and the distance between G and Q, do some Pythagoras. So we need to know F, G, P, and Q. Now, H is completely irrelevant because H just determines the radius of this circle, and it doesn't matter where this circle is. You're looking for the distance between the two centers. So we just need to know about those 4 things there, which will be the answer of B. Question 5, then you've got a line going through 1, 2, which is there. And P is the same one. If the y-intercept is negative, so down here somewhere, then the x-intercept is positive, so over here. And yeah, that makes sense for this line, right? If we're down here and we have to get there, then we have to pass through this line somewhere to get from down here to up there. We have to pass through this line because it's just a line. It's not, there's no discontinuity or anything like that. So this is just true. The converse of P is when you flip those two statements around and keep the if and the n in the same place. Now, if the x-intercept is positive, so if we are over here somewhere, then the y-intercept is negative. Now, that's not true because we can draw a negative gradient line like this. So this is not true. This is not necessarily true. It could be true. There are lines that do it, but it's not necessarily true. And now the contrapositive of P is you flip these things over just like we did for the converse, but then also shove in nots into here. So not negative, not positive. So it looks like this. So if the x-intercept is not positive, i.e. 0 or negative, which is over here, then the y-intercept, spelled wrong, excellent, is not negative, which means positive up here. Well, again, I think that's true, because if we intersect this line over here somewhere, we must pass through this line up here to get to there, right? So I think this is true, and we'll have statements 1 and 3 are true only. Question 6 then, consider the following statements. The number is odd, the list of inches n inches, so the number is odd. The median is one of the numbers on the list. So let's just make this list. This is a list of n integers where n is 4. Now the median here, the median here is 2. The median is in between this 2 and 2, which is 2, and therefore the median is a number on the list, but n is even. So it's not necessary to be odd. So we can cross out the necessary ones because it's not necessary. It can be a number on the list even if there's an even number of terms. Now, if you've got an odd number of terms, like this list here, I wrote some very interesting lists, as you can see, then sure, of course the median is going to be on the list because you literally just select the middle one, which is right here. So it's going to be sufficient, but not necessary, is going to be our answer. Question 7 then. Consider this, the difference between 2 consecutive positive cubes is always prime. Now, this sounds not true because that's just not how primes work. So, okay. Here's an attempted proof of this claim. Okay, sure. Now I said this sounds not true, but let's just go ahead and maybe maybe show that. So 2 cubed minus 1 cubed is prime. I know my prime, so I was basically just taking away numbers here. This is prime. This is also prime. This is also prime. And then the last one that I was actually willing to spend 10 seconds doing was this one, which is not prime. How they fool ya. How they fool ya. So yeah, patterns can fool you. This isn't prime. And so we can immediately get rid of this because the claim isn't true. We found a counterexample. Now, this is complete nonsense. The proof is correct, but there are counterexamples to the claim. That's, I mean, that's not that's not how math works. So we can get rid of that. Let's look through this then. So this is obviously correct. It's just expansion. When you take away x cubed, you're obviously going to get this. That's fine. It's impossible to factorize this into two linear factors because the discriminant is negative. Now that's actually a true statement. The problem is that it's completely irrelevant. So I think the mistake is on this line because this is technically a correct line. It just has nothing to do with what you're doing, right? You can totally factorize it. I mean, this I think involves putting x is 5 into here because that gets, yes, x is 5 gives you 91 here, which is factorizable, right? It's 13 times 7. So the fact that you can't factorize this across algebra is completely irrelevant. And so therefore, this is the incorrect line because it's this is technically correct. You can't factorize it, but it's got nothing to do with the conclusion that they're drawing here. That you can't factorize it because of that. So this is the incorrect line. It's just completely irrelevant. You could factorize this, if you use some complex numbers and stuff like that, which I assume is where this comes from. But yeah, just because you can't factorize this using integer coefficients has literally no bearing on whether or not, when you actually get a number out of this, whether you can factorize it like that. So yeah, the mistake is here with this drawing of this conclusion on line number 4. Yeah, cool. 8 then. So a selection S of n terms taken from this sequence. So the sequence just goes up in threes. I'm going to write the last few before 70 here, because this just demonstrates that when you take two of these to make them equal 74, like clearly this one and this one add to 74, but because this one's 3 bigger and this one's 3 less, clearly these two add to 74, and so do these two, and so do those two, and then they just keep doing that into the middle. Now the middle one is just 37, which doesn't have anything to pair with because there's only one copy of that. So what we can do to take as big a number of terms from this sequence as possible and have none that add to 74 is we can just take them all the way up to 37. That guarantees that none of them add up to make 74 because you haven't got any of their partners in here. And then the moment, now hang on, first there are 13 numbers in this list because this is one more than the 12th multiple of 3, but you start at 0 essentially. So 13 numbers, you can just count them as well. If you add any of the rest of the numbers, then that will pair with one of the things in this list. So the moment you add the 14th number, you'll definitely have a pair that add to 74. So 14 is the smallest number where it's necessarily true that you do that. This one's a bit of a weird one. For all numbers x, if x is less than k, then x squared is less than k. Let's just choose a k, like 50, and ask ourselves whether this is true. So if x is less than 50, so okay, 49, then x squared is less than 50 is complete rubbish. So no, it's not true for all real numbers. Clearly, it's not going to work for 50. And you might be tempted to think, well, okay, this is about squaring, so we need to go less than 1, or between 0 and 1, something like that. If we go less than 1, okay, well, this is fine for 0.5. 0.5 is less than 1, 0.5 squared is less than 1. Amazing. Except you're not bounding this on the other side. So you could just choose x to be minus 3 because it says for all numbers x if this is true. This is true for x is minus 3, but it breaks this because minus 3 squared is 9. So because you're not bounding this on the other side, there's just nothing we can do. Like there's nothing we can choose here. It's just not true for any real number, any number k at all. It could only work if you bounded it on another side and restricted yourself from using negative numbers, which would just square to something much bigger. So yeah, it doesn't work at all. This one's also kind of weird. For all real numbers x and for all real positive integers n, x is less than n. Well, that's obviously not true because, obviously, like proof by obviousness. How are you gonna just pick an x that's bigger, right? Like, pick what? Like, it's just nonsense. It doesn't make any sense. So we'll ignore that. For all real numbers x, there exists a positive integer. This is sounding better already. There exists a positive integer n such that x is less than n. This is true. You can give me any real number you want, any real number you want, and I can just pick a positive integer n such that I'm bigger than you. Like this is the idea that we learned when we're like 5 years old in primary school, where we can just always find a bigger number, right? If we just learn what it's called. So yeah, this is true. There exists a number x such that for positive integers n, x is less than n. So this is just this the other way around. There exists a number x such that for all positive integers n, we can do this. Well, yeah, because for all positive integers n, we could just pick a negative number and we could just make this work because we're not restricted here. It's just as real numbers. So that's true as well. And we'll have 2 and 3 of the true ones. So question number 11 then, this is a kite. By definition, kites have right angles that intersect at 90 degrees, so I'll put that there. And we're asking for necessary and sufficient conditions for SPQ to be a right angle. So that's a right angle there. This is a kite, so this is the same as this. That's also 90 degrees. Now, this kite has opposite angles here adding to 180, and it must therefore also have this angle and this angle adding up to 180 because it's a quadrilateral, so it must add to 360. Now, if it has two pairs of opposite angles adding up to 180, that means that you can put a circle around this kite and do this. Um, a really nice fact about all circle theorems is that they're both necessary and sufficient. They work in both directions. So it's not just if you have a circle and you put a cyclic quadrilateral inside of it, then we have 90 degrees, or sorry, then we have the sum being 180 degrees. It's if you have a shape that has the sum being 180 in both opposite cases, then there's a circle going around it. So that's really helpful to know because all I really need to do now is look through this list of things and look for the circly thing. Look for the thing, like I can change this to, instead of thinking about this kite, I can just think about this circle. And this one screams out to me because this is x squared. That's x times x equals y times z. Now, x times x is here, y times z is here. And you don't explicitly learn this in the UK in GCSE, but there's a really, really nice theorem called power of a point theorem in circle theorems, whereby if you've got two chords like PR and SQ, this length times this length on this chord PR equals this length times this length on SQ. And that just works in circles. And so the fact that that's true, and again, that's a necessary and sufficient condition for two chords to be in a circle and for in a circle with two chords. So that's definitely necessary and sufficient, and we can just underline that as the correct answer because it has to do with this circle here. And we're pretty much done there. We're pretty much done. That's all we need to do. Question number 12. So obviously we don't want to do any actual integration here. What we'll just say is that integrating is about area, right? Between 0 and 1 in all cases here. Now, if you've got two graphs and one is consistently higher than the other one, then this integral between 0 and 1 will be more than the integral of this green one between 0 and 1 because the graph is higher and therefore has more area beneath it. So all I'm going to do here is think about which graph is higher in each case. I'm not going to do any integration. So between this graph and this graph, which is higher up? Now, it's tempting to say this one because you're raising to a bigger power because it's x and not root x, but you're going between 0 and 1. And when you square root something between 0 and 1, your number actually becomes bigger. Like the root of 0.81 is 0.9. And so actually by rooting this x between 0 and 1, we're actually increasing this power, and 2 to a bigger number is just bigger. So this graph here is consistently higher than this graph here, and therefore the integral is greater. Now looking at these two, the root of 2 is smaller than 2. So this is a lower power consistently being raised to the same number, and therefore this graph is lower than this one, and so Q is bigger than R, and we have our chain saying R less than Q less than P, which is this one here. 13 then, so there's a statement, there exists a real number Y such that this is negative for any value of X we want. So let's just try a value of X, let's just try 5. Let's do this turns out to this, and of course there exists a number Y such that this works. Like, of course there is. In fact, there's lots of values of Y that make that work. But there exists a value for Y which I can do that. I think it's unlikely that, I mean, I can rule out this now. I think it's unlikely only one value of X would do that, and I just happened to find it first try. You can try 6, but of course you get something that looks basically the same, and you therefore, I think at this point we can agree, it's either all values of X, or there's going to be just one or two cases it's not. Like there's nothing special about 5 or 6. I could do the same thing with 7 and so on. So I think it's one of these three now. So the question now is, can I find values of X for which I can't do this? And the obvious thing is to try are X is 0. but I think I can do that. I can just choose y as a negative number, and that works. Try x as a negative number, but that also seems to be fine. I can find values of y that do this. There's one value that actually does work, or makes this not work, I guess, which is x is 1. Because if you do that, the y's cancel, and you just end up with this, which isn't true. So I can do this for every single value except for x equals 1, and the answer will therefore be E. Just a case of trying stuff. Now, I talked about in paper 1 how sketching modulus functions is often really good, and how to do that. In this one, actually, I think the best method is just to square both sides, which gets rid of the mod functions entirely. So we can square both sides of this, and we can do this, and then we can, the x squareds cancel, of course. We can do this, and then we can do this. So this is where this is true. You can check that by substituting in and make sure that you found a good value there. Do the same thing here, so just square both sides, cancel the x squareds. You get this. And now we want both of these things to be true. I mean, that's what all these conditions are talking about. So when are both these things true? When are we greater than -8 and less than -6? Well, when you're between -8 and -6. I think that's pretty much that. So this is an interval length 2 in between the two. So for example, x is -7 works, and you can check that, but it does work for both of those things. And we're good to go. Question 15 then is, for me, this was just a case of playing around with it until I got it to work. So, x to the power both sides here sounds like a good idea. I then took log to base z of both sides just to try and get log to base z of x out of this. Bring the z down to the front is, of course, what I did here. And then, yeah, divide by z, and I end up with this expression for log to base z of x, which is fine, but it's obviously not any of this. I need to get rid of this log. So now I started thinking about this one. So again, I can clear out this log by doing y to the power here. And then I think I took log to base z again of both sides. Now log to base z of z is just 1, and this x can be brought down to the front. But of course, this is log to base z of y, which is the thing I was trying to get rid of. So divide both sides by x, and then just put this result into here to get 1 over xz equals log to base z of x, which is this case here. I mean, again, it's just trying. It's just fiddling around with it until you find something that achieves something, and that's all you have to do, really. Just don't be intimidated about it. Just do it. Okay, so we have a series of integers. I'm just making sure I read this right. Oh, who cares? Such that this thing happens. So basically, like A1 is less than B1 plus C1, and A2 is less than or equal to B2 and C2, and so on. But like, it's not necessarily the case that A5 is less than B5 plus C5. Like, you need to choose the same corresponding term from each list. Which these must be true. Just do counterexamples. So you don't need to make lists up to 100 because, like, why would you? And it's not relevant. I just made lists of 3, right? So here's my list for A, here's my list for B, and here's my list for C. Now, I paused for a second because it says 3 sequences, but it doesn't say linear sequences or anything like that. I think I can argue that this is a sequence, and so is this, and so is this. I'm fairly happy with that. Anyway, so yeah, just check. So A1, which is this, is less than or equal to B1 plus C1, so that's fine. Less than A2, less than B2 plus C2, and so on. So that's all good. But the minimum of A1, which is 5, is not less than the minimum of this plus the minimum of that. So this, I found a counterexample for that. This one here, the minimum of A greater than minimum of this plus minimum of this. Well, I just found a case where that was true. But if I just do a more normal case here, like this, I think it's not true anymore. Because the minimum of A1 is just 5, and that's not greater than the minimum of this plus the minimum of that. So that's not true. And then the last one certainly looks more true, right? The maximum of A1 less than the max of B1, max of the B list, max of the C list. Now, the thing about this is, any value in the A list is less than its corresponding sum from the B and C list. But if you're replacing that B here, for instance, with the maximum of B and the maximum of C, you're only serving to make this bigger. And sure, you might be able to make this bigger, but you can't make it any bigger than its corresponding value. So you kind of get into this loop where you can try and, you have A5 less than B5 plus C5. You can try and make this bigger by choosing the maximum of the A list. But the maximum of the A list is still smaller than its corresponding B and C list. So this I think just has to be true by some vague logic, and we'll end up with 3 being the only one that we're going to go for. Question 17 then. I think I've talked about this formula or sort of result in a video before, because it's occasionally quite useful to mirror. But in any case, this person is trying to prove that this cubic equation has three distinct root roots if this is true. So what they've done is they differentiated this, which is fine, to get this, which I also agree with, just double check it all. Solving dy by dx equals 0, well, clearly either x is 0, which gives you that, and therefore y is b, which is fine, or x is minus 2a over 3, which is that, and then you put minus 2a over 3 into here, and you find what y needs to be. And I did actually just double check that, just in case that was the mistake, but it's fine, this all works out, so it does end up being this. It's unusual for them to make a mistake that's just numerical like that. Anyway, what he's going on to do then is he's saying okay, so if this thing here happens is less than 0, then b and b plus this have opposite signs. So, to multiply two things to be less than 0 is either negative times positive or positive times negative. So he's saying that one of these is positive and the other is negative and vice versa. So they have opposite signs. And remember, those are the y coordinates of the stationary points. So he's got two stationary points, one of which is on the y-axis. And if they've got different y coordinates, if one of the y coordinates is positive and one's negative, that means the graph must cut through the x-axis to travel to one and get back down to the other again, right? So in this case, it would cut through it here, here, and then here again, and that's three distinct routes. Whereas if this was on the same side as this one, if they're both positive, then it would cut once through here, but then turn a couple of times and just go back up again. So that's what he's trying to argue here. And he's said that, okay, if this is true, I don't really know where the 27 comes from, to be honest, but sure. If this is true, then they have opposite signs, and so one is above the x-axis, one below. Now it says, if the cubic has three distinct roots, this is a problem. He can't say if that, because that's what he's trying to show. So at no point is he allowed to say if the cubic has three distinct root roots. You have to summarize with that. The whole point of this proof is to finish it at some point with the words, then, therefore, the cubic has three distinct root roots. You can't write if anywhere. So all he's done wrong here is they've just written this statement the wrong way around, right? That they needed to write the converse of this in this step here. Then they would have, I think, been fine, right? They're just not allowed to say the thing that if the thing that I'm trying to prove is true, then this. Like, you're trying to prove that's true. You can't just say, well, if it's true, then go ahead. But that's not how proof works. So that's all that they did wrong there. 18 then. So look at these four graphs. What's the big difference between the four? The most obvious immediate difference is that this one starts at 0. So let's look for which of these graphs starts at 0. So when x is 0, so x is 0 makes this 1 to the power 1, so that's definitely not it. This makes this 0 to the power 0. Now that's, no, 0 to the power 0 is unequivocally 1. And I don't care what anyone else says. But even if you're unsure about that, let's just keep going. This would be 1 to the power 0, which is just 1. And this one would be 0 to the power 1, which is equally unequivocally 0. So this one here must be q. So this one is q sine cos, sine to the cos is q. So we can get rid of all options aside from those two, and we've immediately got it down to a 50-50 in about 10 seconds work. Now, the next most obvious difference is that this one finishes at 0, whereas all of the other ones finish at 1. Now, that looks helpful, except the only options we have tell me that p is cos to the sine, which does indeed finish at 0, because cos pi over 2 is 0 to the power 1 is just 0, but it doesn't help because it doesn't eliminate anything. So essentially what I need to do is decide which one of these two things is this one and which one is this one. Now, to do that, I mean, I thought about differentiating to find the turning point because that's the obvious difference here. However, I didn't feel confident. Well, I feel confident differentiating these two things. But I think in TMUA, you're not supposed to. By the way, there are no work solutions at the time of me recording this, so I'm just kind of winging it. We shouldn't be differentiating this. That's not TMUA things. So what I decided to do instead was just investigate what happens at pi over 6. So at pi over 6, cos of pi over 6 is root 3 over 2. So it's root 3 over 2 to the power root 3 over 2. Sine of pi over 6 is a half. So this is a half to the half. Now, and all I'm really looking for is which one, can I tell which one is bigger? Because the graphs say that one of them should be slightly bigger than the other one. And now this is a lower number to a lower power than this is. So I think very logically, and I don't think I'm getting anything wrong here, I think this is definitely the smaller number. And so therefore S comes from the graph sine to the sine? And the answer is E. And I don't think there's any problems with that logic, although I'm not 100% sure now that I think about it again. But who cares? Let's just go with E. Um, yeah. A polygon has n vertices, where n is bigger each of 3. Of course it is, because you can't make a polygon with 2 vertices, can you? But sure. Every vertex of the polygon lies on a circumference circle C. The center of the circle is inside the polygon, and that's only worthwhile to say because of the next thing that they're going to say, which is, so here's a polygon inside of a circle, which is that the radii from the center to the vertices cut the polygon into n triangles, 4 triangles for 4 sides, all of equal area. Now, if the shape didn't include, if the shape was just drawn over here and didn't have the center inside of it, then this whole lines to the edge thing wouldn't really work. So that's just why this is here. But anyway, all of these radiuses have length r, right? And so to make all of these triangles an equal area, I mean, the area of the triangle is a half AB sine theta, where this angle is theta. So to make these triangles equal area, surely you just need theta to be equal every single time, right? Theta, 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 theta. That would make all of these triangles equal area because the formula is just the same every time. And if all of these equal thetas, then by SAS, all of these triangles are identical, which means all of these sides are the same length, and therefore the polygon is regular. Except that's not quite enough. That's not quite enough to deduce that's completely sufficient. Which of these values at n are sufficient to deduce the polygon is regular? Oh, yeah, sorry. Because it's asking the question slightly the wrong around. You can do some other stuff, like half r squared sine theta equal half sine squared sine alpha does not imply theta is equal to alpha because of the repeated sine values you could get for example, sine 30 equaling sine 150. Like there are certain values you can put into sine to give you the same output. So here's a picture, this one here, where this angle is 30 and this is 150. And now the area of this triangle is going to be the same as the area of this triangle because sine 30 is equal to sine 150. And even more so, the values of sine that give you pairs equal outputs always add up to 180. So like sine 20, sine 160, sine 10, sine 170, sine 40, sine 140, right? They always add up to make 180 because that's just how the sine graph works, right? You're symmetrical around the point 90 degrees in the middle. So you can always make a kind of a straight line here where you have 2 angles that add up to 180, and those 2 triangles are guaranteed to be the same. So I can do this quadrilateral. If I do the same thing on the bottom here, 30, 150, all of these triangles add up to have the same area, if this was 30 as well and this was 150. But the polygon itself is obviously not regular. So it's not sufficient for n equal 4. This is not a sufficient, these conditions are not enough to guarantee that the thing is regular because of this repeated idea in sine. Right? So n equals 4 doesn't work. So it's not all values of n, and it's not this one here. Now, the thing is, though, instead of using 30 and 150, if I use 60 and 120, which is still, sine of 60 is still equal to sine of 120, so this still works, but then put a bunch of 60s on this side, I can make 5 triangles that are the same. And so therefore I can make a pentagon that has equal angles all the way inside, sorry, equal areas all the way around here, but is not regular either. And I can keep playing the same game, right? Like if I went down to, if I wanted a hexagon, I would need 4 triangles on this side, which would mean 45, 45, 45, 45. So then I'd do 45, 1, 3, 5 here. And this would be the odd one out, which would mean it wasn't regular, but it would all hold. And I could just keep doing that. I could keep doing that for any value bigger than 5 or bigger or bigger than. So I can get rid of all of these as options, right? Any polygon with 4 sides or bigger, I can just make not regular by doing this trick. So that just leaves n equals 3. And the reason n equals 3 doesn't work, in other words, a triangle, is because this condition here means you need to get the thing, you need to get the center inside that polygon. But the problem is, as we discussed, for this sine trick to work, for 2 things to be equal in sine that are different, you need those 2 things to add to 180. So you need this length here to go through the center because it needs to be a straight line. But you can't have that if you need the shape to have that center inside of it, right? We just miss it. The closest we can get is like this, but we don't have 2 things adding to 180 here, just about. And so therefore we can't do it with this one here. The only option is to just make angle 60, 60, 60, right? And so therefore it is a regular triangle or equilateral triangle. So therefore n equals 3 is the only one we can sufficiently say these conditions are sufficient for. All the others we can do the trick for and break the rule. Question 20 then. So m1, m2, m3, m5 are the maximum values of each of these functions. Now the maximum value of cos is clearly 1, and it happens when x equals 0, although that's not too important to us. It seems like we can do any range of values we want here, so I'll just go close to 0 every time. Now, sine of cos of x. Now, if you look at the sine graph, you want to get as close to pi as possible, because sine maxes out at 1 if you can input pi, but you can't make cos of x pi, because pi is too big. It's bigger than 1. The biggest you can make cos x, as we just said, is 1. So the biggest input we can put into this is 1. And if we look at that, the input 1, and I know I can do this in a computer, which helps out slightly, but it's just for ease of looking at it. Input 1 gives you a value slightly less than 1. So this maximum is slightly less than 1. And x equals 0, right? Because cos of 0 is 1, and then sine of 1 is slightly less than 1. Okay? Now this one here, if we choose cos to be, I think we choose cos to be pi over 2 here, because that makes cos, sorry, we choose x to be pi over 2, because that makes cos 0. Sine of 0 is 0, and then cos of 0 is 1. And so we end up with a maximum value of 1 here as well, which takes a bit of effort to find. But anyway, we can scroll out this here, right? They're not all equal to 1. The maximums are all equal to 1. We can also, based on this, take out this option and say that it's either, well, it's one of these 4, right? So far, that's all I know so far. Now let's consider this one. We just decided 10 seconds ago that we can make this function 1 if we want to. But we also decided, and notice how that function is just this function here, we also decided that sine of 1 is the biggest we can get sine. And so therefore we would do sine of 1 here, and we get exactly that same result we found in this function here. Because I can make this function the same as this one, and those are just the inputs of this next one. So therefore m4 is equal to m2, and so we're not this case or this case, we're one of these C or E. Now, what's the difference between C and E? Well, C claims that I can just make M5 maximum 1, just like I could make M3 and M1. And E claims that I can't do that. So, okay, let's have a think about this. We need to let's just try and make the maximum of F5 1. Now, cos of what gives me 1? Well, cos of 0 gives me 1. So I need to make this thing 0. Now, sine of what equals 0? Well, that's sine of 0, right? So I need to make this thing here 0, just working back and back and back. Now, cos of what gives me 0? Well, that's cos of pi over 2. So can I make sine of cos of x pi over 2? Well, of course I can't. Pi over 2 is bigger than 1. I can't make sine of anything bigger than 1. And so I can't actually do that. So play back the video if you want to follow that logic again. But I can't, it doesn't seem possible to make this equal to 1 anymore. I could also go back, I claimed that to make this equal to 1, I need to do cos of 0. Now that's not technically true. I could do cos of, say, 2 pi, right? That would also give me 1. Except I can't make sine of something 2 pi either, can I? Because that's way bigger than 1. So this just isn't going to give me 1. And so therefore I can just rule out this as an option, and it's going to give me something between 0 and 1 instead. And so the answer will be E. That's the entire video. Thanks for watching, and I'll see you next time.